Okay, so inorganic chemistry, thermodynamics of coordination complexes. So within this, there's like these topics. There's equilibria, so that's looking at the equilibria involved with ligand exchange reactions primarily. We have the release of energy through Gibbs free energy, delta G, stepwise additions of ligands. We could have, or stepwise exchange even as well. Looking at the stability of coordination complexes, Lewis basicity, steric hindrance, looking at the metal ligands, the chelate effect, and hard, soft, acid-base principles. Some metal ligands form stronger bonds with metals than others. And so a common type is ligand substitution. So here we have a water ligand being replaced with a cyanide ligand. And so that is a stepwise process. We have, of course, the first step where the first water is replaced with one cyanide to release a water molecule into solution. And then, of course, this can have an equilibrium constant because this is not necessarily a one-directional reaction. We can easily go back to the starting materials because there's really been not a lot of chemical changes in the components. I mean, obviously, the complex has changed. It is a new ligand, but all of the ligands are chemically unchanged. The metal is chemically unchanged. So there is the possibility of going back to the original. And this would be our equilibrium constant for that first reaction. However, of course, there are 5 or 6 at the start, but then after the first replacement or first substitution, there's going to be 5 water ligands remaining. And each one of these can also be replaced with a cyanide ligand. So the second step then would be this 5 water complex with one cyanide ligand, and then we would replace another water so that we would end up with only tetra aqua as opposed to 5 waters. Then we would have equilibrium constant for this. Of course, we omit water because typically these reactions are done in aqueous solution. But overall, it's better to use the overall stability constant for a particular system, where that is going to be the product of the individual equilibrium constants. So the process continues. We have until basically all of the water molecules have been replaced, we can develop a equilibrium expression for that and get an equilibrium constant. So this is a stepwise replacement of the ligands. And so for the overall reaction, we have this hexa aqua iron 2 complex is going to become this hexacyanoferrate 4 or ferrate 2 complex. So of course, then each one of these steps has its own intrinsic equilibrium constant, and we can create an overall stability constant for the 6 reactions as beta 6. And that's going to be the product of each one of the individual equilibrium constants given this form here. If we were to multiply each one of these equilibrium constants together, we would find out that this is what we would have. And so the value for beta 6 for this reaction is 10 to the 35, favoring the formation of the complex, the hexacyano complex over the, that should be 4 minus, over the water complex. So in the literature, you often see pK or P beta. And since the reason for this is because the numbers are very large. So for example, in the previous example, the replacement of water by the cyanide ligands, the equilibrium constant was 10 to the 35, or stability constant was 10 to the 35. And so that's quite a large number. So it's usually better to just use log to the base 10. And so we can indicate this using the P, which of course stands for log to the base 10. So we have pH, we have pKa. So since pH is equal to log times the H plus ion concentration, so pK is equal to log K. And so indeed, if we have beta, then we can also get P beta. So another advantage of this is we don't have to worry about the units, because whenever we take the log of something, it becomes unitless. And so the stability constant now, of course, is no longer the product of the individual K values if it's the P beta, but in fact, the sum of each one of the pKa's or pK reactions. So it can relate stability constants to the free energy change. So delta G, so the Gibbs free energy is equal to minus R T, ln K, where R is, of course, the universal gas constant. So from thermodynamics, then we can relate the free energy to the enthalpy and the entropy. Delta G is equal to delta H minus T delta S. And so we can relate the equilibrium to the energy of the process. So here is the replacement of 6 water ligands with 6 ammonia ligands. It would, of course, happen stepwise, but this would be the overall reaction system. And so we can see here, we have where X is the number of ligands which have been exchanged, that as we increase the number of ligands that have been exchanged, the K value gets lower and lower. And that is partially because as we replace more and more ligands, it becomes more and more difficult to affect the next change. So for example, to go from 2 to 3 is harder than 1 to 2. Going from 3 to 4 is harder than 2 to 3. So, and that's also reflected in the free energy. So we have most of these are spontaneous reactions up until the 5th exchange, which is a non-spontaneous process. It requires us to give the system energy, which is why we have a positive free energy change, which means that if we left the system undisturbed in solution, we would end up most likely with tetra amino copper complex as opposed to having the hexaamino. So this is kind of where the reaction would stop. So in a stepwise formation, generally speaking, it follows what I said, where the first step is the easiest. So the pK for the first step is going to be larger than for the second step, and so on, until the lowest pK value is going to be for the last step. So reactions don't always go to completion because we also have to consider the free energy change associated with that. And so we need to ask the questions, why are some metal ligand bonds stronger than others? What dictates the release of energy? So what affects the stability? So we've got basicity of the ligand. There's often a link between the strength of the ligand and its coordination ability. So the ligand NF3 forms less stable complexes than NH3. So NH3 here versus NF3. So the problem with the fluorine substituents here on the nitrogen is that they're very electronegative and they pull the electron density away from the nitrogen, which results in the reduction in the electron density on the nitrogen. And so it's less able to donate electron density into the positive center, metal center. Whereas in ammonia, the hydrogen's not particularly electronegative. And so they don't pull at the electron density in the same way that the fluorines would. Steric hindrance, of course, the ligand has to get near the metal. So if there are bulky substituents adjacent to, or at least near the binding atom, so in this case, the nitrogen, then it's going to be harder for 2,6-lutadiene to get to the metal center than it would be for pyridine here, which does not have the metal groups at the 2 and the 6 position. Then of course there's also the metal involved, so that has a number of potential variables. There's the charge of the metal, there's the transition of the metal, there's the crystal field stabilization energy, and then there's its position in the Irving-Williams series. Chelate effect, so chelate complexes are more stable than monodentate species. So you can see here the stability constant for the formation of this hexaamino nickel complex is a lot lower than the stability constant for this complex formed from a water complex having the ligands exchanged with 1,2-diethylamine or ethylene diamine, which forms this. So the stability constant here is more than twice, and that's because of the chelating effect of these bidentate ligands. So the free energy change is given here. So delta G is equal to delta H minus T delta S. So 6 nickel nitrogen bonds are formed. Hence the value of delta H enthalpy is approximately the same. And so the large effect therefore must be the entropic delta S. So there's 2 ways to do this. There's entropy gain in disorder. So whenever we go from this side to this side, we go from 4 molecules or 4 species, the complex plus 3 ligands, to 7 here, the complex plus 6 ligands. And so that creates more disorder. Whereas in the first one, there's not a lot of, there's no difference, 7 on both sides. So delta S is less. And then here, the enthalpy is going to be quite large, or entropy is going to be quite large, or at least larger. As well as that, you can look at it in the sense that it's kind of hard to remove a polydentate ligand. The reason for that is because if you have a monodentate ligand, if you sever this metal ligand bond, then the ligand can float off into solution. Whereas if you sever that bond in a polydentate ligand, the other bond still exists, and so it's possible for that that ligand to reattach. So applications of the chelate effect analysis, where you wish to participate all of a complex, removal of unwanted ions, for example, calcium and magnesium. Whenever you're doing water softening, you use polyphosphates. It's called sequestration, which is a vitally important process in biological systems. Yes, so like the different types of poisoning can also be treated with polydentate ligands. They're given as a treatment for that because it will sort of like coordinate the metal ions which are unwanted in your body and stop them from potentially causing unwanted reactions inside of your body. Okay. So then how do we determine which ligands are preferred over others? Well, we have to look at a theory called hard, soft acids and bases. So as I mentioned in the acid-base lectures, the acids and bases, Lewis acids and bases, very well describe the bonding in coordination complexes. So Lewis acids accept lone pairs of electrons. So they are the metal centers. So typically the metal centers are positively charged or have empty orbitals, which are capable of accepting electrons. Lewis bases then donate lone pairs of electrons, and these are then the ligands. So, you know, we've got the water ligands with the lone pairs on the oxygen. We've got the nitrogen ligands or the ammonia ligands with the lone pair on the nitrogen and so on. So the metal ligand bond is Ml, and then if we're exchanging that for the new ligand L star, what sort of controls the position of this equilibrium? So the ranking order of Lewis base strengths needs to be compared to the acid behavior of the metal. So ligands form more stable complexes with manganese 2+ and chromium 3+ if they're small, electronegative, and only slightly polarizable, which are defined as hard bases. These metals are small and not very polarizable either, and so are defined as hard acids. So hard acids in general are small, highly charged electron pair acceptors, and hard bases are small, highly electronegative electron pair donors. So soft acids and bases are largely diffuse and polarizable species. So hard acids bind preferentially to hard bases, and soft acids bind preferentially to soft bases. So like prefers like, so hard with hard, soft with soft. And so you can broadly classify metal ions and ligands into hard, soft, and I guess borderline or intermediate criteria. Those that sort of sit in the boundary or near the boundary of a particular class. So hard metals typically are those with a high oxidation state, or the alkali metals and the alkali earth metals. They're all typically hard acids. Then these transition metals with their which are highly charged, like titanium 4+, chromium 3+, cobalt 3+, iron 3+, and so on. Then the ligands, it's those which are sort of near the top of the periodic table, those with highly charged ions. So borderline then are those that sort of sit in the middle. So things like iron 2+. So you can see here iron 3+ was a hard, but then iron 2+ is kind of intermediate. Then maybe iron 1+ is going to be a little softer. And so things here like ruthenium 2+, rhodium 2+, iridium 3+, and then over here on the ligands, you've got things like the nitrogen ligands. We've got ammonia, we've got pyridine. We've also got some things like bromide. So bromide's a little bit bigger than the fluoride and the chloride, and so it typically is an intermediate or borderline acid or base. And then for the soft acids and bases, we have things like cadmium, we've got palladium, platinum, we've got any metal which is not oxidized. Then we have on the ligand side, we've got things like the hydride ion, the cyanide, carbonyl, thiocyanate, and so on. And so these are pretty much empirical, and care must be taken in using them. They do provide a good rule of thumb, so it's possible to compare between the two to try and understand what is happening overall. So hard, soft, acid, base theory. So which ligands prefer to bond to which metals? How can we explain the following? So if we've got a particular complex formation, M2 plus X minus with the stability constant of K is equal to MX plus. So mercury 2 plus and zinc 2 plus show opposite trends in stability with the halides. So for example, we would look at sort of mercury 2 plus and see that the stability of the complexes is going to increase as the ion hardness reduces. So soft ions like iodide typically form the most stable complexes with mercury 2 plus, whereas the opposite is true with zinc 2 plus, which can generally be pretty well described by the hard, soft, acid-base theory. So hard Lewis acids bond preferentially to hard Lewis bases, and soft acids prefer soft bases. So soft acids are, in summary, high electronegativity, at least high for metals. They have large radii and typically low charge, and so they're usually in the bottom left of the D block in particular, or the bottom right, as it is actually. Should be the bottom right. So we've got rhodium, we've got palladium, silver, iridium, platinum, and so on, and then even mercury over here. These are typically soft, and then hard acids are generally the others, or at least the ones that are far from this group of soft metals. So you'll see here intermediates such as technetium, ruthenium, osmium, rhenium, cobalt, nickel, and copper, and then the others are typically hard. So this is the description. This is why we see the pattern that we saw on the previous slide. So zinc is typically a bit of a hard acid. Mercury is a soft acid. And cadmium, these are all in the same group. Cadmium is, I guess, intermediate. It's in between those two. So what we see is that with intermediate, they typically can sort of like form complexes either side of the like either with hard or with soft. They don't really like to. They prefer other intermediate bases, but you can have soft bases. You can have hard bases. It's just the stability here. You can see is more on the soft side than on the hard side, but bromide is an intermediate base, and chloride is on the borderline of hard and intermediate. So these three are pretty stable. The fluoride, not so stable because of the fact that it's quite hard. And then with mercury, it prefers the softer bases because it is itself a soft metal. And then the zinc, then being the hard acid, prefers the hard bases. So the hardness and softness varies with oxidation state, so it's not universal that a metal may always be hard and soft. So some things like, for example, iron and cobalt 2 plus are both intermediate, but then in the case of iron 3 plus, that's hard. Rhodium and iridium 1 plus is soft, and 3 plus is intermediate. It kind of goes that usually if it's going to have variable hardness, that's going to be variant with the oxidation state. So as the oxidation state gets higher, you're going to see a change in the hardness. Generally, the higher the oxidation state, the harder it will be. So again, soft bases, for bases, then soft bases have low electronegativity. at least low for non-metals. They have large radii, and then ligands with things like copper, carbon, phosphorus, sulfur, and so on as the donor atoms. Then hard bases, they have high electronegativities, they have small radii, and they're ligands such as oxygen and fluorine as the donor atoms. Intermediate bases, nitrogen and chlorine as the donor atom. So the donor atom is equal to the atom bonded to the metal. So due to the trends in size and electronegativity in p block, each type lies in a distinct region. This sort of generally helps us to remember them. So those in the top right. So it's also kind of a little bit similar to the electronegativity scale for the Pauling electronegativity. So those with high electronegativity, such as oxygen and fluorine, they're typically hard bases. But then those that are moving away from that center of high electronegativity typically reduce in hardness. So we have here like nitrogen and chlorine, those are intermediate, a little bit less electronegative. And then the other ones here are soft. They are definitely not that electronegative. So chlorine and bromine, or chloride and bromide, I said earlier, the chloride was hard and that bromide was intermediate. Really, they're kind of borderline in both cases. Chlorine is kind of hard intermediate, and bromide is kind of intermediate soft. So they're kind of on that boundary where things start to get a little bit unclear as to exactly which category they should be in. Instead, really, they have properties or ability to behave in both ways. It's kind of like if you have a chemical bond which doesn't really fit. It's the electronegativity difference is not so large as to be ionic, but it's not so small as to be covalent. It kind of sits in that kind of boundary between polar, covalent, and ionic. So the origin of hard soft acid base theory was purely empirical, and it was just based on the observations of the stability constants of the different complexes. But it can actually be explained through the electronegativities. So for example, if we have soft acids, soft bases, we generally see good covalent bonding, whereas those with hard acids with hard bases, there's usually a large difference, and it's more optimal for ionic bonding. And so you can observe that. So we can see here examples of hard soft acid base theory in action. And so that's especially obvious in cases of like things like ambidentate ligands. So we have a choice here of donor atoms. So we have thiocyanate here, which is the SNC or NCS, depending on whether it's bonding through the S, it's going to be thiocyanate. If it's bonding through the nitrogen, it's going to be isothiocyanate. So this is a combination of an intermediate donor, the nitrogen, and a soft donor, the sulfur. The other one is cyanate, which is a combination of an intermediate and a hard. And so you can kind of tell the hardness or softness of your metal based on which one is going to bind to the metal center. So you could do experiments to look to see which bonds are actually involved with that complexation. And so that would be able to tell you if your metal is hard or soft. So if you look at these sorts of complexes, you can actually try to predict the bonding modes based on the type of metal ion. So for example, in this complex, we have trimethylphosphine, that 3 should be a subscript, bonded to gold. And then the binding of the thiocyanate is through the sulfur, so it is still thiocyanate. And this is primarily because this sulfur is in fact soft. And so the gold is a soft metal. It will bind through the sulfur atom. Then over here, we can see that we have a combination of titanium. Titanium typically is a hard metal, which means it's going to prefer hard acids. However, in the case of the thiocyanate ligand, we don't actually have a hard donor. we only have a soft and an intermediate. And so what ends up happening is that the binding is through the intermediate nitrogen as opposed to the soft sulfur, because ultimately intermediate is closer to hard than the soft would be. And so we see that it is binding through the nitrogen. It is therefore an isothiocyanate ligand. Here we can see the complexation and the different complexation modes of acetylacetone or ACAC, the acetylacetanoate, or ACAC. It's basically easier to say ACAC. Is a ligand which can also have different binding modes based on whether or not the metal is a hard or soft metal. So the reason why it's capable of doing this is because of the delocalization of the negative charge across these two carbonyl groups here, which also encompasses this carbon. So this carbon is part of this system, which means that this carbon is capable of acting as a ligand. So if we put this ACAC ligand in with cobalt-3, we see that it acts as a bidentate ligand. So cobalt 3 plus kind of a hard oxidation or kind of a high oxidation state, most likely going to be a hard acid. The oxygens then are hard bases. And so we see that it acts as a bidentate ligand, coordinating to the cobalt metal center. If, however, we combine it with this gold 1 is a soft metal center, similar to the gold 1 we saw on the previous slide, it is not going to want to interact with the oxygens very much. The oxygens are too highly charged, they're too small, they're not really very polarizable. It just doesn't like the sort of combination there. And so what ends up happening is that it acts as a monodentate ligand and it binds through the carbon to the gold center. Predicting ligand exchange reactions can also be done based on hard, soft acid-base principles. So if we look at and try to classify the different ligands on the metal centers. So here we have a metal center, which is platinum. So platinum is on the, I suppose, softer side of the metals. It's got a combination of intermediate ligands. So it's got the nitrogens and chlorides, a little bit maybe on the harder side. And then we're combining that with, or seeing if the ligand exchange reaction will occur, which will exchange the platinum for the phosphorus. And so we have to sort of look at the phosphorus and say whether or not that is a hard or a soft ligand. And so the phosphoruses typically are soft. And then we would be looking to see whether it will exchange with the nitrogens or with the whether the nitrogens would be replaced. So whether this reaction would take place. The nitrogen ligands also being kind of intermediate. So what's most likely to happen is that the reaction would most likely proceed, that we would probably see the replacement of the ligand by the phosphorus ligand, this triethylphosphine, because of this sort of like combination of hard, and soft, or intermediate, depending on what it is. So hard, soft, acid-base theory in biology. So ions such as lead 2+, mercury 2+, cadmium 2+, and tellurium plus are all highly toxic. These are all soft metals. The reason why they're toxic is they bind to sulfur sites in proteins and stop them functioning properly. So cysteine here is a semi-essential amino acid. And so this has different sulfur sites, which could be bond or could have binding occur between them and one of these metals. We also see hard, soft, acid-base theory in geology. So the classification of different mineral deposits is kind of based on whether or not it's contains sort of like hard acids and bases or soft acids and bases. So things like in geology, the geological classification of elements, lithophiles found as cations and oxides, silicates, sulfates, and carbonates are things like aluminium. So aluminium oxide is also known as bauxite ore. Titanium is found as rutile, titanium dioxide, and magnesium is found as magnesite, which is magnesium carbonate. So here we have different, so we have SiO2, SO4 minus, so we've got sulfate, carbonate, oxide, and the silica. Chalcophiles then are cations found in sulfides, so silver sulfide, argentite, and then mercury sulfide, which is cinnabar. So lithophiles are typically hard acids, so oxides, silicates, sulfates, and carbonates, these, so hard bases. So anything with these ions in them are typically going to be lithophiles, and then chalcophiles are those which are soft acids that are attracted to things like the sulfides. The chelate effect that we've talked about before, let's talk about it in some more detail now that we know and understand a little bit more about hard, soft, acid-base theories. So chelating ligands, i.e. those that bind, those binding through more than one atom, generally give more stable complexes than analogous monodentate ligands for the reasons that we discussed earlier. The entropy rather than enthalpy is mainly responsible for this effect. So 4 molecules become 7 molecules. So this was the, or similar to the reaction that we saw earlier. This was water earlier, it's now ammonia. So these, this hexaamino nickel 2 complex is having a ligand exchange reaction stepwise to replace the ammonia ligands with this 1,2-ethylene diamine. And so that is of course successful. It's got a negative free energy change, which is the result of a positive change in entropy because we have the movement from 4 species or 4 molecules to become 7, and so that is obviously contributing to the general disorder of the universe, and so that is favorable. So the chelate effect can also be understood by imagining the anchor effect of the chelate. That's something we also looked at. So if one bond breaks, the other holds it close to the metal, and this increases the statistical chance that it will re-coordinate. Other common chelate ligands are the trine ligand, which is tridentate, and then ethylene diamine tetraacetate, EDTA, which is hexadentate. So it has binding sites. Typically, this is found as the tetrasodium salt. So usually, like each one of these acid groups has been neutralized by and reacted to form the sodium salt. So there's no hydrogen ions here. And this just improves the ability for the ligand to be activated so that we have these hard binding sites with the oxygens, and then we have these intermediate binding sites through the nitrogens. So EDTA forms very stable octahedral complexes, and it's used in chelation therapy. So for example, the removal of excess copper for Wilson's disease. So it's a World Health Organization, I think, essential medicine, EDTA, because of its ability to be used to remove heavy metal ions from the body. Well, unwanted heavy metal ions. Although sometimes you remove also the ones that you do want. So chelating ligands such as the diphosphines, these are important as ligands for transition metal catalysis. It won the Nobel Prize in the year 2000 for these phosphine ligands. They're important for things like industrial hydrogenation reactions. They're good for the formation of catalysts, which will provide single enantiomer reactions and so on. You can design them to really give you the product that you want in your reaction. So we have diphos here, and then we have binap, which is a very it is a very common ligand. So one of it's not totally planar. This one side sort of points towards us and one side sort of points away from us, or sorry, the bottom part, this part points towards us, this point parts away, and this part towards us, and this part away. So that these phosphoruses are slightly displaced in space. And this is because these two naphthalene rings are kind of sterically hindered from each other, because there's only they're actually bound together by this carbon-carbon bond. But the so the sterics of this mean that it cannot be planar. And so this is binap because it is a binaptally ligand. So the macrocyclic effect is part of how some of the chelating ligands work. So if we compare two ligands, which one is a macrocycle and the other is just open, then the macrocycle is generally going to give more stable complexes. And so this is usually due to entropy. So like if, for example, I look at this reaction where I have this palladium complex, which is coordinated by 4 different nitrogens. This ligand here is a long chain ligand, whereas if I compare it to the cyclam, it is a macrocycle. So the cyclam is capable of also binding the palladium metal. Then the nitrogens are arrayed in a manner which is similar to what we see with the long chain ligand. Now, the cyclam, however, will result in a complex which is more stable because there is a low entropy for that ligand. It sort of is stuck in that one position because of these carbon chains which connect the nitrogen centers together. It means that there's not a lot of flexibility in conformation for this molecule. It also means that whenever it would bind that metal, that if we did have a break in the nitrogen palladium bond, that the nitrogen, so whenever you've got that multi-dentate ligand, whenever you break that bond, like one end is attached and the other can kind of like, it's nearby, it's still tethered, but it can sort of move a little bit freely. If we were to break the bond here between the palladium and the nitrogen is still going to be here because it cannot move very much because it's anchored by these other 3, which means that it's even easier to form this bond again. Whereas if this bond is broken, this nitrogen can like sort of rotate around here, over here, anywhere in this area here, or even all the way up to here if this were to rotate freely. So it can cover a huge area, which means that it's harder. I mean, it's easier than a monodentate ligand to reattach, but it's still harder, much harder than it would be for this. So again, due to entropy, so when coordinated, both ligands are conformationally locked in space. There's little freedom and low entropy. But when released, the non-cyclic ligand is more flexible. It has greater disorder and greater entropy. So we can see that here in the schematic. So the macrocyclic effect. So we have this ligand is coordinated, or this metal is coordinated by 4 different centers. It's kind of like the nitrogens on the previous page coordinated to that palladium. And so they have 4 bonds. And then if we were to remove the metal, we would still have the same shape for the ligand. It did not change. Whereas here, the metal is acting as a structure directing agent. And so the shape of the ligand is dictated by its coordination sphere to the metal. However, if we remove the metal from the center of this, you can see that the ligand becomes much more flexible. It kind of will move about in space with a great degree of disorder. So it's flexible, it has more disorder, and it has higher entropy. So the loss or the breaking of this complex is easier to do than the breaking of this complex. Some naturally occurring macrocyclic ligands. So we've got the porphyrin rings. So some examples of this are 2 very important molecules, one for mammalian life and the other for plants. So the heme porphyrin ring is an important part of hemoglobin, and hemoglobin is important for the carrying of oxygen through the human body and through other mammalian bodies. So it is similar to that cyclam that we saw earlier, but slightly different. It has 4 nitrogens which will coordinate to a metal, in this case iron. How this generally works is that the iron is only coordinated on 4 sides, and so it's capable of accepting 2 more dative covalent bonds. And typically what happens is that there are nearby counterions for times when oxygen is not coordinated here, but if oxygen is coordinated here, then that is going to take precedent. Then magnesium porphyrins are similar to the iron porphyrins, except obviously they have magnesium in the center rather than iron, and they are important in chlorophyll, which is of course an important molecule for the conversion of carbon dioxide into oxygen. Template synthesis, so we can use some of these ligands to actually influence the outcomes of chemical reactions. So this would be through template synthesis. So the reactions here, which connect together ligands whilst attached to the metal, ligands are pre-organized by attachment to the metal and make synthesis of macrocyclic chelating ligands more efficient. So we can do, for example, a shift-based reaction, the formation of an imine directly on the catalyst. In fact, that's how some catalysts work, is that they coordinate the reactants to the metal center as if they were ligands, and then while they're coordinated to the metal center, they are then capable of reacting and forming a new molecule, which then maybe does not have as good an attachment to the metal and can be lost into solution. Or even if it's a monodentate ligand, like those things are just sometimes fall off anyway. Template synthesis then. So we have here the desire to form a ring between this molecule and this molecule. So the thing about it is that it's possible for this nitrogen to react here and form an imine, and then a different molecule to react on the other side, and then to form a long chain, almost like a polymer. However, if we want to create a ring every single time, the best way to do it would be to have a metal ion, which can be a structure directing agent via the complexation of these 2 molecules as ligands to the metal center. And so that's exactly what you do. So if you've got no metal ion, you get a mixture of chains and rings. But if you do have a metal ion, then the metal ion can sit in the middle and can coordinate the oxygens here and the nitrogens here. And then the nitrogens and the oxygens, or sorry, the nitrogens can then bind or react to form the imine whilst attached to the metal center. And that will cause the formation of the macrocycle to happen with much greater reliability. Then you can remove the metal with strong ligands such as cyanide to liberate the macrocyclic ligand. So you just use a different ligand, a ligand exchange reaction, even though this is a macrocycle. So long as you give a ligand which has a more preferential binding, you can get the metal out again. So ligand steric bulk, so we talked about this before as well. So some ligands take up more space than others. So for example, here I have a phosphorus ligand, trimethylphosphine. You can see here the phosphine, or the phosphorus is the purple sphere. And then we have tri-tert-butylphosphine. And so this has a much more steric bulk to it, at least the ligand substituents. And you can see that the amount of phosphorus which is present and therefore able to get close to a metal is much lower. And you can see here also that this almost totally covers the phosphorus. So it would really need to be a very open metal with very few ligands, or the other ligands would have to be very small for you to get good complexation between this ligand and a metal center. So space filling pictures are useful to understand size and sterics. And so atoms shown as spheres at their van der Waals radii. So you can see here that this is sort of like this angle here is called the Tolman angle. And so you can see it's pretty good for the phosphorus, trimethyl phosphorus. But then for the tri-tert-butyl phosphine, it's almost 180 degrees or less than 180 degrees. Not very good for the formation of a complex. Okay, so what I was talking about there in the previous slide, this idea that there could be an angle of availability of the coordinating atom. It has a name, the Tolman angle or the cone angle. Can roughly be, it's a good guide. It's not a perfect guide for whether or not a ligand will bind to a metal, but it's a pretty good guide. So bulk can be roughly quantified with the cone angle theta, devised by Tolman originally for phosphine ligands at PR3. He made a model and drew straight lines from the metal to the van der Waals surface of the ligand, assuming that the metal phosphine distance of 2.28 angstroms, which had been observed as a pretty good average for various metal phosphine complexes. And so the Tolman angle for different phosphine ligands is given here and compared to things like what do you call this? Carbonyl ligands. You can see that the Tolman angle, as the Tolman angle gets larger, it's going to be harder for this metal phosphine bond to be formed. So the trimethylphosphine is much easier to form than triphenylphosphine, which is much easier to form than tri-tert-butyl phosphine, which we would see through. You could do like stability constants and whatnot for this as well. And then carbonyl is just given as an indicator of a ligand which is quite small. Its Tolman angle is around about 90 degrees, and so it's very easily to fit it around a metal. So the effects here means that some ligands will form more stable complexes than others. So bulky ligands prefer to be mutually trans, as this minimizes steric congestion. So if we have these two bulky ligands beside each other, they're going to sort of like hit each other, and so they're not going to like that. Whereas it is possible for the trimethylphosphine because the Tolman angle is smaller than, for example, the Tolman angle in the tri-tert-butyl phosphine, where the bulky ligands prefer to be trans to each other because otherwise they just get in the way of each other. And typically with these sorts of ligands, you can only really have low coordination numbers. So for example, here, if we can have a tetracarbonyl nickel 0 complex, we can only have, for example, a tris triphenyl phosphine nickel complex. And then if we get an even bulkier ligand, we can only have a di complex, a tri-tert-butyl phosphine complex. So remember, however, that cone angles are only really rough indications of steric bulk. Ligands are actually more flexible than it seems, and that's also not a perfect cones of, also not perfect cones. Ligands can intermesh in the coordination sphere. So like they can overlap, like the methyl groups can sort of interlink a little bit. That's kind of okay, and it does happen.